In this lesson, we're going to continue our look at the reactions of enols and enolates, focusing on alpha-halogenation reactions. Most enolizable carbonyls can undergo alpha-halogenation under acidic conditions. In the example, we see acetophenone halogenated with bromine in the presence of an acid catalyst. Notice that in this example, the product could potentially undergo further alpha-halogenation. Two alpha protons still remain that could undergo substitution. However, acid-promoted alpha-halogenation typically results in monohalogenation, replacing only one alpha hydrogen. If we look at the mechanism, we see that the first two steps are just an acid-promoted enolization. In the first step, the carbonyl oxidant is protonated by a strong acid. In the second step, an alpha proton is removed, resulting in the formation of an enol. The pi bond of the enol then attacks the dihalide, assisted by a lone pair on the adjacent oxygen. In the last step, the newly formed carbonyl is deprotonated to give the final product. Most enolizable carbonyls can also undergo alpha halogenation under basic conditions. In the example, we see propiophenone halogenated with bromine in the presence of base. Unlike acid-promoted alpha halogenation, base-promoted alpha halogenation is typically exhaustive, substituting all alpha protons with halogens. In this example, we see that both alpha protons of the reactant have been replaced with bromine atoms. The reaction mechanism begins with base-promoted enolization. In the first step, an alpha proton is removed by a strong base to give an enolate. In the second step, the pi bond of the enolate attacks the dihalide, assisted by a lone pair on the adjacent oxygen. These two steps are then repeated until all alpha protons have been replaced with halogens. Exhaustive halogenation occurs under basic conditions because the alpha protons of the product are more acidic than those of the initial reactant. The newly added halogens stabilize the negative charge formed during subsequent enolization. This makes the enolate formed from the product more stable than the enolate formed from the initial reactant, driving the product towards exhaustive halogenation. So if you've ever thought organic chemistry is hell, well, today you're right, because the next reaction is the Hell-Volhard-Zelinski reaction. This reaction is simply the alpha halogenation of a carboxylic acid using phosphorus tribromide. In the example, we see propanoic acid treated with phosphorus tribromide and molecular bromine, giving the alpha brominated product. The overall reaction is just the sequential combination of three reactions you've seen previously. The transformation of a carboxylic acid into an acyl halide with PBr3, followed by acid-promoted alpha halogenation, and finally hydrolysis of the acyl halide via acyl substitution with water. Fortunately, this means that the reaction mechanism is just the sum of those three reactions. We'll wrap things up with a look at the haloform reaction. The reaction gets its name from the fact that it forms a haloform, a trihalomethane such as chloroform. The haloform reaction converts methyl ketones selectively into carboxylic acids. If we look at the example, we see acetophenone treated with an excess of molecular bromine in the presence of base, forming benzoic acid and bromoform. The reaction is unusual because it actually cleaves a carbon-carbon bond. The haloform reaction using iodine was once used as a qualitative laboratory test for methyl ketones, which would react to give a pale yellow precipitate of iodoform. Treatment of an unknown substance with iodine and base would result in the formation of a precipitate only if the unknown were a methyl ketone. The reaction mechanism involves exhaustive base-promoted alpha halogenation followed by an unusual acyl substitution. Once all three alpha protons have been replaced with halogens, the carbonyl is then attacked by hydroxide, which now serves as a nucleophile. The trihalomethyl group is then expelled as a leaving group, cleaving the carbon-carbon bond. Ketones don't usually undergo acyl substitution. Displacement of an alkyl group would form a highly unstable carbanion. In this case, the three halogens on the alpha carbon stabilize the resulting carbanion via electronic induction. This allows a small amount of the carboxylic acid to form, which is immediately deprotonated by the carbanion to give a resonance-stabilized carboxylate. This places the negative charge in a much more stable position and drives the reaction forward thermodynamically. The reaction is then quenched with an acid, which reprotonates the carboxylate to give the final carboxylic acid product.